All right, so here's a sextant I bought 1973, and after sailing for a couple of years, I saved up some money. It's a German sextant, Plath, which was pretty good at the time. So basically, sextant is really just a protractor, and so you can move with a movable arm here, and it has a mirror that reflects from the celestial body down to this glass here. And if you can see it, this glass has got a clear half and a mirrored reflected half. So what you do is you point it at a celestial body, you bring it down to the horizon, which you can see on the left-hand side of the mirror, and the reflected body is coming down on the right-hand side, and you have a clear horizon. So what you need to have is both the ability to see the body, the star or sunlight or whatever, and a clear horizon. So you need them both at the same time. So what you would do is you bring the body down, you get the angle, and then you swing the sextant, you rotate it like this, so that the body swings like a pendulum, and you get just the very bottom of that swing to touch the horizon, and then you take your sight, you get your time. Typically in the old days, you'd have a stopwatch in one hand, and then you'd click your stopwatch to give you the amount of seconds it takes to go back to the chronometer, and you look at the chronometer, stop your stopwatch, and then back off the amount of time it took you to get the sight. So this also has, for sunlines, it has these shade glasses. That one's for the horizon, and this one is for if a sunline, you would want the shade glass for the sunlight. So you can move it here, and then you have the micrometer that moves here. So pretty slick. Yeah, so that's all you basically do. Like I said, you get the body there, you swing the sextant like this to get that celestial body swinging like a pendulum. When it's right at the very bottom, that's your sight. You leave the sextant angle to where it is, and then you go back and check your time.
So the way you read a sextant is, you can read the degrees. There's a pointer on the scale.
Yeah.
You read the degrees off of your pointer, and then over here, this is called a tangent screw, and it's a little worm screw that will, if you just keep cranking it, it'll just go over and over a degree. 1 revolution equals 1 degree. So when you get it exactly lined up, you read the minutes off of that dial. And then if you think you're really better than you are, and at sea, there's a vernier scale where you can get the tenths of minutes.
Yeah, right off to the side here. So.
And if anybody around here could shoot an angle to a tenth of a minute from a rolling deck.
Yeah, you're out there, the wind's blowing, the ship's rolling a little bit. And, yeah, on a smaller boat, you're trying to hang on to make sure you don't
And
go
those talking about
yeah.
the arc. The reason you do that arc thing is because, especially if you're on a heeled over sailboat, you want to make sure that your sextant is perfectly vertical, because we're measuring from the horizon perfectly vertically up to the celestial body. So by rocking it back and forth, if it goes up that way and up that way, then you're at the right spot.
At the right spot.
And having gotten that degree, you now look at a set of tables, right?
You're making the transition for me.
Yeah.
So,
That's
how does celestial navigation work? Like that. If you imagine this funnel doesn't have the stem on it, and the sides just go all the way up to the top. So imagine yourself standing on this blue marble now and looking up. You see the circle where the funnel actually touches the ball is a circle on the surface of the planet. Anywhere on that circle, that celestial body will be direct, it's directly over the point of the funnel. So the angle that you would measure from anywhere on this circle is the same.
But that's also going to vary seasonally because of
Yep. Okay, so back to the tables, etc. There's a book called a Nautical Almanac, and that tells you what you basically need is and I won't use the celestial terms, but you need the latitude and the longitude of the object. There's some place on the Earth that object is directly over. Where if you were there, it would be exactly overhead. You could turn around and around and you would always measure 90 degrees. So you figure out where that place is, you find the angle that you measured, and then some very complicated spherical trig, which has all been done. A guy by the name of Bowditch first did the work.
Okay.
And, well, he did it most comprehensively, I should say. There have been people doing that work since the chronometer was invented. But the state of the art is called HO, Hydrographic Office 229. It's a series of books about that thick that have essentially worked out every spherical trig problem there is. And so you work your way through the tables until you find the observation that matches. So basically what you're doing, if you want to get a celestial fix, is you do that and you have one circle of position. You shoot another object and you have another circle, and where they intersect is where you are. Which brings you to the practical matter of celestial navigation isn't useful unless you also have some idea where you are.
Yeah, you're using a swing position to go into the table.
This great big circle is treated in the math as a straight line, because if you're on this tiny little dot right here, you look at that circle and it looks like a straight line. This circle is, potentially thousands of miles in diameter.
The intersection of two circles, though, is actually 2 points, and only one of them makes sense, right?
Yeah, exactly.
So you have to know roughly.
But even beyond that, you need, in order to enter those tables and look up the complicated math, you need to know where to look in the table. So you start out, you figure out the geographic location over which your celestial body is sitting, and then you enter the tables to find out, based on your assumed position, to find out how to correct your assumed position. There are a couple of interesting cases. One of them is Polaris, because Polaris it's not exact. It's about 1.25 degrees off of the actual true North Pole of Earth. So it goes around in a really, really tiny little circle, and the corrections are fairly trivial. If you know what time of year it is, pretty much, you can look those corrections up directly. You can get your latitude from that almost exactly, because if you're at the equator and you can see Polaris, then you're at the equator. You would measure 0 on your sextant, which is the other challenge, of course, because you'll never see Polaris when you're at the equator. It will be in the sea smoke, or you just won't see it. You almost will never see Polaris when you can see the horizon. So handy as it is to be able to shoot a Polaris angle, you might have 5 or 6 days a year when you could actually do that, because Polaris is a fairly dim star, and by the time you can see the dimmer stars, the horizon has disappeared. You need a really sharp horizon line to get a useful celestial fix. So typically the stars that are used, to the extent that people use stars, are like Aries and Orion and
Sirius.
Sirius,
The brighter the star, the better it is.
The first magnitude stars, I can't remember. I used to remember that there are like 7 or 8 that are the ones you typically always use, and because they're the ones that you're likely to see when you can still see the horizon. But you can always see the horizon, assuming you have a clear day, when the sun's up. So the other trivial solution, and the one that actually predates even chronometers, is getting latitude from the sun. You know that the sun moves it moves from 23 degrees, 23.5 degrees north of the equator to 23.5 degrees south of the equator. But you don't need a stopwatch. If you have a calendar, you know what day it is. You know almost exactly what it's called declination, which is the equivalent of longitude, or latitude rather. It's the latitude over which the sun is shining directly down.
Okay.
So what you do is you go out and stand on deck and you keep shooting the sun every couple of minutes.
Watching it, and you're
over and over and over again. If you don't have any idea what time it is, what you want to find out is what's called local apparent noon. The sun comes up over there somewhere, goes up, and then it starts down. If you capture that moment with its maximum altitude, and then you figure out what the correction is for north or south of the equator where the sun is, with simple arithmetic, you get your latitude. And before there were chronometers, one of the ways that you found someplace was you sailed to that latitude and then sailed due east or west until you hit it.
Okay,
So
okay.
that's why the sextant has all the filters like.
Yeah.
Yes, you can look at the
You
sun.
can look at the sun. You can also look at the moon, which
Yeah.
you can see the moon many times while the horizon is still visible. Sometimes you can see it in daylight, depending on where the moon is and conditions. But so that's why the filters are there, because sun is one of the easiest ways to take a fix. And you can actually take a fix when the sun is not directly overhead. You can use it like you would use a star.
You're right, yeah.
You find the spot that it is directly over, and then you measure the angle and correct it. And perhaps one of the most common for single-handed sailors and things like that are going to struggle to get star sights is you take what's called a running fix, which is to say, sometime in the middle of the morning, you shoot the sun and you get a circle of position. You know you're steering, the course you're steering and the approximate speed you're making by keeping track of your speed log and so forth. So what you do is you move that position around. So you get one position, and then you'll get another position later in the day, and then you advance the previous one by the distance and speed that you've traveled, and you'll have a reasonably good fix. 5 miles, 10 miles, something like that. It's not going to be great, but it's going to be way better than not knowing where you are.
You know, hang on just a second. I wrote something down here, and
You can do advancing fixes with some coastal navigation too.
Oh yeah. That's a common way of, if you got one lighthouse and it's the only thing you can see, take a bearing on it, sail 5 miles on a known course, take another bearing, and advance them, and you have a reasonable cross. Not super accurate, but again, better than one land position.
so yeah, just to go over some numbers. So if we went out today, you're on a ship, and you're going to observe local apparent noon. It actually happens. It comes across our meridian at 1:14. So the reason it's not at 12 o'clock noon is, first of all, the time zone. We advanced our clocks. That's 1 hour. The second thing is we're not on the meridian, the central meridian. We're a little bit west of it, so it's going to take a little bit longer for the sun to come across. And the third thing, which is kind of minor, is just the equation of time. It's just, it doesn't go across the meridian right at noon, even in Greenwich. So if we went out there and we took a sight, we would get something like 67 degrees, 30 minutes of altitude, okay? So if you subtract that, the altitude from 90 degrees, you get 22 and a half, okay? So we know we're north of the sun because we're facing south. We know what the declination of the sun is. It's 23 degrees now. We just had the summer solstice. So like Mitch said, at the solstice 9-10 days ago, the sun was 23 and a half degrees, but it's coming back south now. Summer's over. So it'll come across the equator in September 21st. So you take that declination, the sun being 23 degrees north of the equator, and you take the complement of the angle, the co-altitude of what I had, 22 degrees 30 minutes. You add those two together and you get our latitude, the 22:30 and the 23, and you get 45:30. So basically, if you were looking at the sun, it's bearing due south, you're not going to see it overhead unless you're at latitude 22:30, okay, down there south of LA. So you take the complement of that angle and you just add it to the declination, because as you went further south, those 22 degrees and 22 degrees 30 minutes, then you would have it directly over the head. So you just have to adjust your, or just add your co-altitude to the declination, and you've got your latitude.
And by the way, the degree of difficulty goes up as your celestial body goes up. So
Yeah.
if you were trying to get a local apparent noon at 22 degrees north right now, it would be nearly impossible.
Yeah.
The sun is going to be exactly overhead, and you have to keep spinning in a circle until you read the same angle all the way around before you would be sure that you were facing the right direction at the right time.
Yeah. You put your arm out, and if the shadow comes right down alongside of you,
Yeah.
you know what your latitude
So
is.
it's pretty easy to get something up to about 30 degrees above the horizon. And the higher above that you go, the more difficult it is to get the sextant level and get a good height above the horizon. As it gets into the 80s, most people just can't do it. I can't.
Yeah. No, it's just,
You would want to, if you're on a very clear night, when you know exactly that you're going to be able to see all the stars you want, try to pick 1, 2, 3 that are nearly at the same height and somewhere around 30 degrees or less. And that's going to be the easiest possible fix.
yeah.
So does that mean when, in the evening, if you're looking for the stars, but you still have to have enough visible horizon,
Yes.
so you're,
Yeah.
Which is
It's like
why,
trying to get
one,
back
you
to
don't use a
sunset.
lot of lights on deck on a ship when you're doing celestial navigation. And second, you tend to go for the first magnitude and sometimes second magnitude stars. Because, second order, because when you get to fourth order magnitude like Polaris, it is just, I think I see it. And then when you finally say, yep, that's it, I can't see the horizon at all.
If you get a really bright full moon, you can sometimes see enough of a horizon out at sea where there's not a lot of lights around. You get a really bright star and you get a bright full moon. You can see the horizon out there and you can get a fairly decent sight.
Other times when the
But
temperature
yeah, most
conditions,
of the time.
you'll lose the horizon almost at sunset because of sea smoke.
Yeah.
You can't pick out a line anymore because it's a layer of haze that, well, to the naked eye, at the horizon it looks like it's an inch tall. It's actually.
Would it work to send somebody out in a boat with a lantern? Horizon?
Well,
That's actually a clever idea.
That brings up an interesting. We didn't talk about corrections, but one of the corrections you have to make is for height of eye.
Oh, yeah.
Yeah,
So,
because the higher you go up.
If you're
further
standing
away.
on the flying bridge of a big freighter and you're 120 feet off the water, your horizon is about 15 miles further
So
away
that'd be
than
a
somebody
long way
who's
to
sailing.
send somebody in a dinghy.
The distance to the horizon, this is kind of interesting. If you take the square root of the feet of your height of eye, that's the square root in feet is about the distance to the horizon in miles. So if you're on a ship and say you're 49 feet above sea level, you're 7 miles to the horizon. And something interesting too, so if you're approaching a lighthouse that was, say, conveniently 144 feet, so the square root of the height of that is 12, and your height of eye is 49, 7. As you're approaching the light, I did this as a cadet, you see the loom of the light. You don't actually see the light itself, but you can see this loom. And you say, oh, that's the lighthouse. You go up to the flying bridge and you can see the light, and you come back down to the bridge, and as soon as you can see it at your height of eye that you know, 49, you say, okay, I'm 7 feet from the horizon. That light at 144 feet high is 12 feet, so I add the two together. I'm 19 feet.
And in a little sailboat, it's really easy. It's called bobbing a light.
And then you walk over to the radar and you check it and you say, oh yeah, I am 19 miles off.
In a
Or
little
you can
sailboat,
tell that
when you're
first
going
step
up and down,
yeah.
in the swells, your height of eye in a sailboat is probably about 4 feet.
4 feet.
So that gives you 2 miles to the horizon that you get while you're sitting in the cockpit. And then you bob up and down, and when you just see that lighthouse, you know you're 14 miles from it.
So I don't know if that's where the term came from, but why wouldn't you shoot the moon instead of a star?
Oh, you
Oh,
can.
you can, yeah.
Yeah,
Oh,
that's one of the other corrections I was going to talk about. When you shoot either sun or moon, you have to correct for the diameter because they're big enough to have a measurable angle. Stars, for all practical purposes, are just a point of light. The moon, you have to shoot upper limb or lower limb. And the moon is the one that can most challenge you. Sun, you just always shoot lower limb. It's easy. The moon, It may not have a lower limb.
Lower limb, right.
It may have only an
Ooh,
upper
ooh,
limb
ooh, ooh.
because of the current phase of the moon.
Yeah, yeah,
So
yeah.
you have to have a correction, and what you're doing is you're correcting. It's a fixed correction for all practical purposes. It changes, you know, the supermoon when it gets closest to Earth, but it's like a minute or two of arc. It's almost negligible. But the correction is, I can't remember now. Is it?
No,
I think it's like 11 minutes across the diameter of the.
Wow, wow, wow.
You know, I can't help but think of those poor 10-year-old midshipmen having to remember all this shit.
Well, you know that there was a lot of memory aids, you know, just old sayings that teach you CGA, Coast Guard Academy, computed greater away. And what that means is that if the angle that you computed for
yeah,
for
you're
a star,
right about it, yeah.
you went out and you measured it, now you went back to doing your paperwork, and you're computing at what height it should be if you were where you thought you were. You're not. If it's greater, then you're further away from the star. So there are all kinds of things like that that the midshipmen would learn so that they could
So they could fudge.
internalize that stuff.
But yeah, no, it just.
I always thought that when you just as a person, you're standing on the beach, that the horizon was 12 miles, so it's a lot closer than that?
It's closer than that.
It is. I never realized that.
Yeah, you can see over the horizon considerable distance,
Yeah.
and you know you can always tell that.
Yeah, you see the mast of a ship.
You'll see the mast of a ship, but not the hull, for
Yeah,
example.
right.
Well, I always thought that when I was a kid, well, when I was in high school, and I lived on the Jersey Shore, back in the days when the big liners, you used to see them come out of New York, and you never saw the ship, but you could see the
Right.
funnels.
That's called hold down.
Yeah, it was really
The
cool.
term hold down
Queen
means
Mary and
it's
Elizabeth.
over the horizon where you can see the rig, but you can't see the hull.
Yeah.
Okay.
But
So the one thing Mitch mentioned, you really need accurate time on a ship. So I guess Magellan was using new insights in getting latitude, but it wasn't until the 1700s, I read this last night, that this guy John Harrison invented the marine chronometer. And there's an interesting book, Longitude. I don't know if we've got it in our library.
It's been made into a movie as well. And the movie's
Yeah.
fantastic.
Oh, I didn't
Yeah.
see the movie. But,
Yeah, it has been. It was a pretty good movie too.
Yeah.
They jerked this guy around for about 40 years to withhold his prize. British were losing so many sailors. Their navy had a big disaster over somewhere in the Mediterranean.
Gibraltar.
In
They
Gibraltar,
sailed
yeah.
into all the ships sailed into Gibraltar.
Yeah, and
2,000 soldiers were
2,000
were lost.
sailors. Wow. So what they put his prize up for like 20,000 pounds, and this was in the mid 1700s, 1730 or something like this. So this guy, he was a watchmaker and just a really clever fella. He ends up building this chronometer, which was accurate to within a second a month, but it was large, and the story is they withheld it because they said, well, this is not really practical. They're very expensive. They're too large to put on a regular merchant ship. We can't put them on all the Navy ships. So they didn't give him his prize. They ended up, instead of giving him 20,000 pounds, they gave him about 8,000 pounds. And it was after about 40 years. It was 3 years before the guy died. And this guy died at 76 years old. So he waited this whole time. And he had a really great invention there. But it was
One of the interesting things about chronometers, you would think, well, a quartz clock would be better. There was a good reason why now people just use GPS because it is the best time signal there is. But then there's no point in celestial navigation if you got GPS either. But the chronometer, even a bad chronometer, has a consistent gain or loss. So they would be calibrated. You would know this is something that the quartermasters on a ship used to do every single day. They would get a time tick over the Navy radio broadcast and check the chronometer's daily rate. So if it's been, your radio went out and it's now been 3 weeks since you last had an accurate time signal, if you know that your chronometer gains 4 seconds a week, you add 12 seconds, you're there, or subtract 12 seconds and you're there. A quartz clock has a much smaller error, but it's random. It's quantum physics, you know, and quantum physics has a certain degree of randomness in it. So it may be 2 seconds faster or 2 seconds slower. That's 4 miles of error. Because that's the interesting thing about the I don't know, you know, I'm sure that they're related in the way that time was invented, but or the geography was measured. A mile is a minute. If you think about from the equator to the North Pole is about 5,400 miles, which is 90 times 60.
Huh.
I have a precision timekeeping chip, and they're 1 microsecond a month.
Mm-hmm.
And it's laser calibrated, so you do have some error there.
Yeah.
But they've worked really hard, the Swiss company worked really hard
Yeah.
to get these really high quality chips.
Yeah, there are plenty of time signals available that are more accurate. The chronometer held on into the, I would say, the 70s.
Yeah, we used the chronometer.
Maybe even the 80s. Well, we had them on the Coast Guard ships into the 90s, but I don't remember. Whether, you know, I don't remember ever having counted on them for anything. But they held on because they had that predictable rate.
Yeah, and look,
They would
it
be
said-
sent off to the Navy Observatory every 5 years, and they would,
Yeah.
you know, calibrate, clean, and adjust them, and record their daily rate, and then you would confirm the daily rate daily.
Yeah, and as long as you knew what the error was, it was no big deal. Yeah, because it would go 2.5
Yeah.
minutes, you know, and
Yeah, you never at sea.
Yeah.
You never changed the dial.
never tried
never-
to
you
correct
never
it.
corrected
You just
your
record
clock.
it so that when you took your sight, you just looked at the clock. Oh, it's fast by 2 minutes and 20 seconds. You just, you know, apply that to your time, and you have the accurate time. So
Before the real good chronometer, you know, they had clocks, but they were really bad. They were minutes off
Right.
within days.
Yeah, that was the big challenge to creating the chronometer is that its mechanism is unaffected by doing this now. A pendulum clock, which is the best clocks they had at the time, are extremely accurate if they're really anchored down. But even a train car was too bad for them. And when you start doing this number, forget it. So that was the trick to getting the chronometer that worked, was that it has to be unaffected by temperature and motion.
Probably moisture as well.
Yeah.
yeah,
So that just made it an extremely challenging engineering problem. And as Bill said, the guy that invented it was the one that got screwed.
Mitch, when you were sailing, did you ever have to shoot off the Southern Cross? Which you were below the equator?
No. Well, my actual sailing experience came far after, you know, GPS was there. And
No. Yeah, but just for the heck of it.
My Coast Guard career, I've been many places where I could see the Southern Cross, but never used it for navigation. It would be easy to do.
Okay, yeah.
But you can only see it. You can begin to see the Southern Cross. It's not like Polaris. It's not right over the right over the pole.
But it's fixed.
But you have no. It actually circles. the
Oh,
pole.
really? Oh,
Yeah.
wider
Yeah,
up?
because it's off by about. I think it has to be at least 15 degrees off true south.
Oh, okay,
Because
wow.
you can see it in Hawaii, and you wouldn't be able to see it at 11 north.
Okay.
Unless
okay.
it was around 15 degrees. You can only see it part of you know. You can't always see it because half of the year it's in daytime when it would be above the horizon.
Mitch, I took social navigation 40 years ago or something. And I remember we had the older books and we had to do a correction for the age of the book. Remember
Yeah.
that? Because I remember the deck students, they got new books, and because we were just taking the class, we got the old books. and we had to do
That's the
a correction.
nautical almanac.
Oh, yeah, the
Yeah,
nautical
your
almanac.
site reduction tables, the HO229, it's good for infinity.
Okay.
It's just spherical trig worked out and, you know, to minute decimal places for every possible problem. But the nautical almanac is what tells you, not to get too complicated, but what they do is they actually, they have what's called a sidereal hour angle. So you have the local hour angle of the body that's equivalent to its longitude. So this book gives you the local hour angle of Aries. Yeah. every minute of the year. And then you can work out the sidereal, look up the sidereal hour angle, which is the difference between the hour angle of Aries and the body of interest. So it's a two-step correction. And that nautical almanac is published every year and is good just for that year. That's, you're entering, looking up the date and time to find out where that star is. And obviously next year, that calculation is completely useless.
Not completely, because you were able to do
So
corrections.
they gave us, there was a correction we did for being a year out or 2 years, whatever it was. And it's less accurate than having the current ones, but it was what we did so we could get the readings, and we were on the campus, so we were good.
So the nautical almanac has, I think about 100 selected stars, the hour angle of Aries, and complete sun and moon tables, and it's about that big.
Yes, it's an inch. And now it's all done on computer.
Yeah. What Bill was saying, he's got an app on his phone.
Yeah,
Um,
on my
which-
phone, it does the calculation.
It does the calculation. It also has an extremely
Wow.
accurate time signal because it uses GPS.
Yeah.
So, perhaps, what's the point of the name of the app? You can also read the latitude and longitude off of it.
Yeah.
Oh, okay, yeah.
Yeah, GPS time signal is accurate to nanoseconds.
You have to
So-
have a sextant to like.
And it's constantly updated. The entire network is talking to the control center in Alexandria and just constantly being corrected so that it really has changed time at sea completely.
So
Is
before I
celestial-
left the company I was working for, it's been years since the GPS has been out, but we have a sextant on all of the ships. And I would go and ask the captain, hey, have you got these mates still using the sextant? Because you never know when the GPS goes out,
Yep.
especially nowadays when they're talking about jamming signals and things like this.
Okay.
So, yeah, we still use the sextant. They still learn it in the maritime academies. how to
Okay.
Use the celestial navigation. So it's a good thing to know.
It's also, the skill of coastal piloting is something that they teach at the Naval Academy, the Coast Guard Academy, the Merchant Marine. All of those professionals learn coastal piloting, even though you never use it anymore.
Okay.
Yeah.
I mean, you've got this, now they have what they call a ECDIS, the electronic chart
Electronic
display.
chart display.
It's like a color TV, a big screen color TV with you on it, a nautical chart display with you on it. And well, because they have collision avoidance systems, every other ship around you is on it. Their name, their course, their speed, it's all there. But that doesn't mean you don't learn a whole lot of the lore of how people used to do it.
Okay, yeah.
So they're having a problem that people are turning off their AIS for various reasons. Because they don't want the Coast Guard to know where they are, they don't want people to know where they are.
Yeah.
They may be
Selling
doing
Russian
something
oil.
illegal, they may be, they may be going out fishing and don't want the other fishermen to know where they are. So we're having this problem where we're having collisions between ships that are relying on AIS and ships that are
Ooh, yeah.
that are avoiding AIS.
I don't remember what AIS even stands for, but it was, my wife and I, when we were out sailing in a small sailboat, in the shipping lanes and stuff, we said, okay, we're not buying each other Christmas presents this year. We're gonna buy presents for the boat. I got a 45-pound Rockna anchor, and my wife got an AIS.
The AIS is great. I think it's automatic identification system.
Yeah, and anyway, what it does is, even for a tiny little sailboat, now I'm actually showing up
Okay.
on the big screen TV on that ship, because sad to say, they're not looking out the windows much, and they hardly look at the radar anymore because they're counting on those systems. And we would over and over, try to get in contact with somebody, you don't really know whether they even know you're there.
Right.
Yeah.
And you want to make sure that they do. I don't care how close they want to sail by me on one side or the other, but I want to
Yeah.
be sure that they know I'm there. With the AIS, they know.
If you're looking at the big screen.
If they're looking at it, right?
Well, they're all looking at